Hello guys, it's Lingzels here, and today we'll be continuing boron. Now, with that out of the way, let's get into it. Chapter 3, Boron's Properties. Actually, what does this mean? Let's get the part. Matter has characteristic properties that have identified. Physical properties can be detected about transforming one substance into another. For example, melting one piece of boron, it changes from a solid into a liquid, but it's still boron, so melting temperature is physical property. It's a physical property. Other properties may be chemical properties. Chemical properties involve the way a substance changes or doesn't change in reaction to other substances. The way an element combines with other elements is controlled by the valence electrons. This is the chemical property. Finally, boron has nuclear properties. Features of its nucleus that set it apart from other elements. Physical properties. Pure elemental boron, which is never found in nature, has several forms. Amorphous, uncrystallized, boron in the dark brown powder, while crystalline boron, a brittle solid, becomes in many different crystal structures, including black, red, and yellow. The properties cited in this section refer to the element's most stable form, the black crystalline structure called beta boron. As a metalloid, boron does not conduct electricity or heat as well as a metal like copper, Cu. But boron conducts better than a non-metal such as sulfur. If you were to hold a lump of the crystalline form of boron in your hand, it'll feel a bit lighter than a typical rock of the same size. This measurable property of a substance is called density, which tells us how much mass we can fit into a standard volume. In chemistry, density is given in grams per cubic centimeter. Boron's density at room temperature is 2.34 grams or centimeters by the power 3, I think. At least that's what I think the small 3 is for. In comparison, the density of pure water is 1 gram or centimeters by the power 3, which is at least what I think the 3 is for. The melting point of boron is 3,769 degrees Fahrenheit, 2,076 degrees Celsius. And its boiling point, the point at which liquid boron turns to vapor, is 7,101 degrees Fahrenheit, 3,927 degrees Celsius. Crystalline boron has exceptional hardness, ranking 9.3 on the most 10-point hardness scale. The most scale was invented to rate material hardness from ranges from 1 for talc to 10 for diamond. Elemental boron is harder than almost anything except diamond. Elemental boron has several forms. Amorphous boron left is a dark brown powder, while crystalline boron is brittle and has several colors and structures, such as the black form on the right. Chemical properties. Although boron is a simple element with only 5 protons and 5 electrons, it can combine with other elements to make extremely complicated structures in ways that they're not fully understood. Boron is difficult to isolate because it melts at high temperature, where it is also very reactive. At high temperatures, boron reacts rapidly with metals, hydrogen, oxygen, carbon, and halides. Group VIIA or 17 elements such as chlorine, Cl, and fluorine, F. And the atoms in these compounds are held tightly together in place by sharing boron's free valence electrons. This kind of link involves the sharing of valence electron pairs between the two atoms that each contribute electrons to the link or bond, which is called a covalent bond. The other elements in boron's group, IIIA, or 13, are considered metals and tend to form ionic bonds, which involve the attraction between positive and negative ions. These group members, aluminum, gallium, indium, and thallium, typically give up a valence of electrons to gain a positive charge and favor links with elements or compounds with the corresponding negative charge. Boron's common bonds can be unusual. In a typical common bond, a valence electron from one atom is paired with one from another atom. This pair is then shared between the two atoms. However, in some cases involving boron, the resulting valence pair is spread across three atoms, two of which are boron. This arises because boron outer electron shell is not full, so it has the capacity for additional electrons. In a special free atom bond, each of the two boron atoms use this capacity to share one electron pair among them and have another atom, such as hydrogen. This leads to boron clusters that can have 12 or more boron atoms combined into very stable K-like structures. The most familiar boron compounds are borides, which are boron-oxygen combinations. Commonly useful examples of these are boric acid and borax, which we discussed earlier. Borax we discussed at the beginning. Ish. We discussed it ish. Boric acid I just forgot. So you can have to watch the whole video. Do not skip through. Nuclear properties. Boron has 13 isotopes, each of which has a unique number of neutrons ranging from 2 to 14. Two of these are isotopes. Boron 10 with 5 neutrons and boron 11 with 6 occur naturally and are stable, while the rest are radioactive with a very short lifetimes. In radioactive isotopes, the nucleus changes all by itself. No outside help, this change usually transforms the nucleus into another element, and the change could cause decay because given the time older radioactive. That would be B2H6 has unusual covalent bonds. Dual boron B atoms share 2 electrons found in the dark green regions with one hydrogen H atom and share another electron pair light green region with another hydrogen atom. All the radioactive isotope will be gone. A measure of decay in the half-life tells how long it takes for half of the isotope to undergo that process. The radioactive boron isotopes all have 5 lives of less than 1 second. Most boron isotopes, including the stable ones, are created when cosmic rays, nuclei, and the nuclear properties ejected from some stars scatter heavier elements such as carbon, nitrogen, and oxygen. Boron is also produced when stars eject carbon, nitrogen, and oxygen, nuclei that shatter when they collide with nuclei and nuclear particles. These two processes are called spallation, occur in the depths of interstellar space and closer to home. What do you mean by home? All beryllium and most lithium are created this way. The other elements were created when the universe began, hydrogen and helium. In stars, most of the rest, or in laboratories. Boron 11 is the most plentiful stable isotope, making up 80.4% of the elements on Earth, compared to boron's 10's 19.6%. While most substances containing boron have this isotopic composition, some physical and chemical processes can favor one isotope over the other. Boron 10, the lighter isotope, is good at capturing neutrons from cosmic radiation, or in nuclear reactors. After capturing the neutron, it splits and produces a gamma ray, an alpha particle, and a lithium nucleus. Boron stable isotopes. Although B11 is more plentiful than B10, the relative amounts of the two isotopes vary considerably from place to place. Our current understanding of boron creation from shattered heavier elements says there should be 5 B11 atoms for every 2 B10 atoms. Instead, for reasons not fully understood, Earth and the solar system have about 8 B11 atoms for every 2 B10 atoms. In addition, small variations from this 8:2 ratio occur in response to temperature, pressure, acidity, and molecular structure. For example, B11 in seawater is about 40 parts per thousand, more plentiful than average, while in continental rocks, B11 is found at relative levels that are within 5 parts per thousand of the average. The stable non-reactive boron isotopes have 5 left and 6 right neutrons, gray and red spheres. About every 8 boron atoms out of 10 are boron 11, and the other 2 are boron 10. Chapter 4. Where can boron be found? Boron is rare, but its compounds can be found in rocks, soil, and water. Wait, doesn't that mean you're drinking blood? Usually in small quantities. Okay, good. Okay, good. Large deposits of boron compounds are in Turkey, parts of West United States, Russia, and several South American countries. Why is Turkey named Turkey? Commercial deposits of boron minerals are generally found in arid areas with a history of volcanism and hydrothermal activity. Lava, volcanic ash, and hot springs can bring the boron to contain compounds from other rocks to the surface. A process called leaching. The deposits in southern. Oh, wait, no. I went too far. Did I? But it can accumulate over millions of years. Sometimes they form in the form of borites. The deposits of southern California's Death Valley took about 2 million years to form, starting 19 million years ago. The boron was leached by rain in a hot spring from volcanic flows and acclimated by a lake that eventually dried up to form deposits in the dry region. Oh no, I didn't know I lost my place. Oh. The deposits were slowly buried, winding up about half a mile, 0.8 kilometers below the surface. The entire area was uplifted by geological forces about 6 million years ago, and brought near the surface again by erosion. Smaller amounts of boron compounds may be found in hot springs near Florence, Italy, were a primary source of boric acid and borax, or Europe, about 200 years ago. In addition to deposits in hot springs, new boron is being created all the time. By spallation? In use in the atmosphere, rocks, and water, but amounts too small to be of use. This giant truck can hold up to about 240 tons of borite minerals, which are dug from huge open pit borax mines and then taken to nearby processing plants. The trucks are usually shipped in pieces and then assembled at the mines. Yeah, has 1 gram more than 240 tons. Eh? Mining and processing boron. Today, the mining of borax and related borite minerals is done from open pits, where the deposits are buried a few hundred feet below the surface rocks and dirt. Geologists base the pit locations on the mineral type and purity of samples taken from the drilled holes. Once a suitable mining location is found, the surface rocks called overburden are removed by blasting in the Mojang desert mines. The overburden is mostly sandstone, The mojave mines are developed with steps or terraces, a pit face to keep the walls from collapsing. At the bottom of the pit, gigantic mechanical shovels about 150 feet, 46 meters high, scoop up 80 tons, 23 metric tons, a bitter weight of 40 cars, and row of rubble and ore, and dump it into. Just like can hold 240 tons. 218 metric tons. The trucks are 20 feet, 6 meters high, and 40 feet, 12 meters long, and drive on 12-foot high, 4-meter tires. The truckloads are crushed into 1-inch pieces for refining. The crushed ore is mixed in hot water to dissolve boron minerals, leaving behind rocks and other solids. The borate solution is then pumped into a large tank where smaller solids settle out, or if there's dirt. The borate solution is then pumped into large tanks where smaller solids settle out, leaving the borate-rich fluid floating on top. This fluid is pumped to another tank to cool, causing the borates to crystallize, forming a slurry of crystals and water. The slurry is filtered and washed and then dried. The resulting borate crystals are stored in silos and domes until shipped elsewhere for further refinement and possible conversion to other compounds and products. Usage of boron. Pure elemental boron has few uses, mainly because it's difficult to isolate, except at high temperatures. Where it prefers to form compounds, most of the current applications for elemental boron rely on isotope characteristics. Boron mining then and now. In contrast to the highly automated operations today, borate mining in the late 19th century was laborious and tedious. Surface deposits were hand-raked, and underground deposits were shoveled and picked, often in hot desert temperatures that took a toll on the people and animals doing the work. In 20-day round trips from Death Valley, teams of 20 mules hold 20 tons, 18 metric tons of refined borate to the nearest train depot. Today, it will take 250 mule teams to move the ore processed in a single day at the borate complex in the Mojave Desert, for example, in the Mojave Desert. A sample of the borate ore, borax, is also called tin cow. It's pictured here. It is also one of the most abundant borate sources in the world. The large deposits are found in the United States and Turkey. For example, compounds that incorporate clusters of boron atoms have been the subjects of recent intense research because they form three-dimensional structures that may be useful for delivering atoms or molecules to a target, such as the cancerous cell. Lost my place. Boron 10, an isotope that captures neutrons and then radioactively decays. Is used in this manner for an experimental treatment to kill cancer cells. The treatment is known as boron neutron catcher therapy. Uses a boron 10, an enriched compound that furtherly concentrates at tumor sites. The boron nuclei capture neutrons from a beam directed at site and then splits into helium and lithium nuclei. This process releases energy to damage the tumor cell, while sparing neighboring healthy cells. This allows much lower levels of radiation to be used when treating than with traditional cancer treatments because the energy that kills the cancer is generated within the cell, rather than being beamed into the cell from the outside. Boron 11, on the other hand, is indifferent to neutrons, making it useful where the effects of the radiation are not desired. Like near nuclear reactors, depleted boron, consisting of boron 11 alone, is used in some glass that protects some semiconductor electronics. Boron 10 is excluded from the glass because stray neutrons could shatter the nucleus, releasing particles and energy that could cause data loss and electronics damage. And now, and that'll be it for today's video. Hope you guys enjoyed, and I'll see you guys again very, very soon. Later.